While we've been looking at differential equations of the form ay double prime plus by prime plus cy equal to 0, I'm now going to consider when it's equal to a function that is not 0. And I'm going to consider 4 different types of functions that f of t could be. The first type I'm going to consider is when f of t is equal to ktm, where k is a constant and m is a constant that is greater than or equal to 0. The second type will be of the type k times e to the rt, where once again k and r are constants. And then we'll also consider k times sine bt, as well as k times cosine bt. So we'll consider all these different things for f, and then we'll also consider products of these for now. And in a later video, we'll look at sums of these 4 things right here. Let's start with this one, where my f of t is just a constant. So I have y double prime plus 3y prime plus 2y equal to 3. The fact that this is equal to a constant here might tell us that y is just equal to a constant, since this involves y and its derivatives. Well, y prime would just be 0, since the derivative of a constant is 0, and y double prime would also be 0. Well, then I have y double prime, which we just said was 0, plus 3 times y prime, which we said was 0, plus 2 times y, which I said is of the form a, equal to 3. So we have 2a is equal to 3, or a is equal to 3/2. So this tells me what my function is. My solution would be just the constant function y equal to 3/2. And this is going to be true anytime this number right here is a constant, then we need to start with y equal to a and solve this equation just like this. Making this slightly more complicated, so I only changed one thing in this problem, which instead of a 3, I wrote a 3t. In the last problem, since I had a constant on this side, I let y be just equal to a constant. Since I have a t here, it might occur to us to just let y be equal to at. In that case, the derivative would just be a, and my second derivative would be 0. So I would have y double prime is 0, plus 3 times y prime, which is a, plus 2 times y, which is a times t, equal to 3t. So whenever we look at these kind of things, we set coefficients equal. So here I have a 3a, and over here my constant doesn't seem to exist. We can think of it as plus 0. So this would tell me that 3a is equal to 0, or a is equal to 0. However, my t's tell me that 2a is equal to 3, since the coefficients need to be equal, which would tell me a is equal to 3/2. And so this causes a problem because a cannot be both of these at the same time. So that tells us what we chose for a here wasn't quite right. So let's try again. So instead of just letting y be equal to at, what we really need is at plus b. Then my first derivative would just still be a, and my second derivative would be 0. The idea is we need to consider what this thing is, as well as all of its derivatives. And the derivative of at would just be a, so a constant, and then all the rest of the derivatives are 0. So now I have 0, plus 3 times y prime, which is a, plus 2 times y, which is at plus b, equal to 3t. This gives me 3a plus 2at plus 2b equal to 3t. And we start with coefficients of t. The coefficients of t on the left are 2a. They need to match the coefficients of t on the right, which is 3. So this tells me a is 3/2. On the other hand, if I look at my constants on the left, I have a 3a and a 2b. And on the right, I don't have any constants. If you want, you can think of it as a plus 0. So we have 3a plus 2b is equal to 0. We already know a is 3 halves, so I have that 9 halves plus 2b is equal to 0. That tells me 2b is equal to negative 9 over 2, or b is equal to minus 9/4. So my solution, 3 halves t minus 9/4. So this would be the solution to this differential equation. In general, if we had something else of the form ay double prime plus by prime plus cy equal to, let's say, 5t squared, then in this case we would let y be equal to at squared plus bt plus c. And once again, we would do the same thing. We would take the first and second derivatives, stick it in, and set coefficients equal. In general, if f of t is of the form k t to the m, then we know that y is going to be of the form am t to the m plus a m minus 1 t to the m minus 1. We continue this until we get to a1t plus a0. So we essentially just build a polynomial of the same degree with general coefficients, and then we do this process.